Good morning and welcome you all to this session of the course on fluid machines. Now, in the last class we discussed the velocity triangles of a typical impeller blade of a centrifugal pump, and we derived the expression for the head imparted to the fluid by the centrifugal pump or the impeller of the pump, and the head developed, and the difference between these was recognized as the losses due to fluid viscosity, and the ratio of these two, that is head developed by the pump to that given to the fluid by the impeller, was defined as manometric efficiency. So, today we will discuss the most important feature of a centrifugal pump, that head discharge characteristics. Let us write then head discharge characteristic, head discharge characteristic, head discharge characteristic. Let us consider an impeller as we already shown earlier, and part of an impeller. I am not drawing the full one. This is the center of rotation. Let the impeller rotate like this at the angular velocity omega. This is the eye of the impeller, part of the eye, and this is the impeller outlet. And we consider an impeller blade like this, as we discussed earlier. Now, here the outlet velocity triangle remains like this. This is the outlet velocity triangle. This is V r2, the relative velocity at the outlet, which was already discussed earlier. This coincides with the impeller blade angle at the outlet, which we defined as beta 2. This is the absolute velocity direction. This angle is defined as alpha 2 by the nomenclature. This is the flow velocity at the outlet, Vf2. So, this is the tangential component of velocity at the outlet, and this is obviously the rotor velocity at the outlet. So, the rotor velocity at the outlet, and this is like this defined. How to draw this triangle? Vr2 is, as I have told, V2 minus U2. That means Vr2 plus U2 is V2. You see, the Vr2 and U2 in the same direction, and V2 represents the other side of the triangle, but in the opposite direction. This way you have to draw the velocity triangle. That inlet velocity triangle, I draw it here, is like this, where we do not want any swelling component of velocity. So, it is in the radial direction, this is the tangential direction. So, this is Vr1, this is U1, and this gives the V1, where this is the beta 1, which is 90 degree, because Vw1 we want as 0. This was discussed earlier. So, now we come like this: theoretical head, that is the head. Let us consider first not theoretical head, as we discussed that the head, that is energy per unit weight imparted to the fluid or given to the fluid by rotor, is Vw2 U2 by G, because Vw1 is 0. Now, if we consider the manometric efficiency eta m to be 1, that is 100%, means if we neglect the viscous effect or the losses due to viscous dissipation, neglect that, then we can tell that the manometric efficiency 100%, the head developed by the pump equals to Vw2 U2 by G, manometric efficiency 100%, and this is termed as theoretical head. So, therefore, theoretical head is Vw2 U2 by G. Now, from this velocity triangle you see that Vw2 is U2 minus this part, which is Vf2 cot beta 2. Now, again we see that U2 is pi d2 n2. And what is Vf2? Vf2 is can be written in terms of the flow rate Q divided by the cross sectional area or area normal to the flow velocity, which is area normal to this velocity. This is flow velocity, which is pi d2 times the width of the impeller at the outlet. So, this is area. For a given impeller, this is fixed. So, now we can write H theoretical is equal to U2 into U2 minus Vf2 cot beta 2 divided by G. Now, if we put these values of U2 and the Vf2, we get that U2 square, that is pi square d2 square n2 square by G minus U2 Vf2, that means pi 2 d2 n2 divided by A G cot beta 2 into Q. These two terms I made the bracket. Now, for a given impeller of a centrifugal pump, D2 is fixed. Moving with this N2 is N actually, pi D2 N. This is N. We have written unnecessarily N2. There is no suffix required because the impeller rotates at a constant speed N. So, therefore, pi D2 N for a given rotational speed, this is local gravity. For a given impeller, the outlet angle is also fixed. So, therefore, these two are constant. So, therefore, H theoretical can be written as K1 minus K2 Q, where K1 is equal to pi square d2 square n square by G and K2 is equal to pi, sorry, here also to pi not pi square, pi d2 n by Ag, pi d2 n by Ag, okay, into cot beta 2. So, this is true that this is given by K1 by K2, pi d2 n cot beta 2 by Ag. So, this is K1 and this is K2 constant. So, therefore, we see under the theoretical conditions neglecting the viscous effect, we can express, and this trend will be same, that means H theoretical is decreasing with Q, and under theoretical condition it is a linear variation, linearly decreasing with Q given by this equation. The head developed is equal to K1 minus K2Q, K1, K2 are given by this. Now, if we draw this in an HQ plane, H the head, Q here, then what this thing, this is the theoretical, this is a curve 1 which we tell as theoretical head. Now, if we recognize one by one all the things that happen in practice or all the practical features we take into consideration, first we take slip, as we defined slip as the phenomena that happens because of the pressure difference at the leading and the trailing sides of the blades, for which there is a circulation and non-uniformity of velocity in the blade passage, which makes the which reduces the tangential component of flow velocity at the outlet and reduces thus the head developed or the energy imparted to the fluid by the pump, and this slip phenomena is independent that of viscosity, and it is purely the influence of curvature of the blade, and this is 0 when the flow is 0, and at low flow this is low. This is a monotonically increasing function of the flow. So, therefore, in consideration of this slip, we know that we can write the developed actual head developed is equal to VW2 U2 by G into sigma S, where sigma S is the slip factor. Sigma S is the slip factor which we defined earlier as the actual VW by the ideal VW. Okay. Now, with this, if you draw, this is increasing with flow rate, the curve is diverging, take care of that and draw this H, then this is the curve 2, which is H in consideration of slip, and at any point means at any value of q at any point in the abscissa, this is 1 minus sigma s into H theoretical, this gap each and every point. That means this is shown by the dotted line. This curve represents H in consideration of the slip head after consideration of this slip. Now, I will consider two other losses. One is the shock loss. What is the shock loss? As I have told earlier that the blades of any turbo machines or fluid machines is designed in such a way that at the design condition, the fluid at inlet and outlet should match the angle of the blades or vane at inlet and outlet respectively, so that it can glide the blade at inlet and outlet. But at off design conditions, when the flow is less or more than the design flow rate, what happens? This condition is not met. So, what happens? The velocity relative to the fluid is not gliding the blade at inlet or outlet. That means, the angle of the relative velocity differs from that of the blade angles at inlet and outlet. Physically, what does it imply? The fluid obliquely enters the blade and it impinges the blade, because of which there are eddies created and which reduces the mechanical energy, through which a part of mechanical energy is dissipated into intermolecular energy. This we see as a loss, and this loss in mechanical energy is known as shock losses. And therefore, this shock losses is proportional to the square of the velocity, as it happens always that any mechanical energy loss due to frictional effect of the fluid, that is viscous effect, is usually proportional to the square of the velocity in turbulent flow regime. And this is square of the flow rate, since the flow velocity is proportional to the flow rate, and this can be expressed in terms of some constant K3 into Q minus Q d whole square. Why? Where Q is the off design flow rate and this is design flow rate. So, this always gives a high value whether this Q is less than Q d or Q is more than Q d, and this is a scalar quantity, this is the energy. So, another, apart from the shock loss, there is another loss of energy, which is the frictional loss in the pump. That means, in the impeller and in the diffuser and in the volute casing. Volute casing itself is the diffuser, is the frictional loss, which can also be expressed in the turbulent regime as square of the flow velocity or square of the volumetric flow rate. So, if everything is expressed in terms of the flow rate, which is common and same through the entire pump, then we can show this first one, that shock loss is like this. That means, this is 0 at the design flow rate, and this attains a very high value when the flow rate tends to 0. While this one HF, the frictional losses, which is 0 at the 0, this is curve 3, this is H shock, and the frictional losses, the curve is like that. That means, this is this equation, HF is K4Q square, this is curve 4, this is frictional loss due to viscosity. Shock loss is also due to viscosity, but the phenomena is different. Now, if you take care of these two from this head, that means, if you subtract these energy losses from this head developed in consideration of this slip, that means, geometrically if we sum at any abscissa, sum the ordinates of the curve 4 and 3 and deduct that from curve 2, we get the final head discharge characteristics, which is like this, and this is the final HQ curve, final HQ curve. This you get by subtracting these two from this head at each and every flow rate. So, finally, this is the HQ characteristics, which comes from a theoretically linear one in consideration of slip, shock and the friction in steps, so that one can draw. And this way you will see that the relationship of HQ looks like this in a centrifugal pump. Now we will consider the influence of or effect of, which is another important thing, outlet blade angle on this HQ curve. Effect of outlet blade angle on this HQ curve. Already I have written it for your convenience. Now there are three types of blades which are being defined, which can be used. One is this type, where the curvature of the blade is in the direction of the rotation, which is known as forward facing vanes. And here the velocity triangle will be like this. You see, this is the VR2 matching the blade angle and at the outlet. This is under ideal conditions, that means design conditions. So this is matching with the outlet impeller angle. This is a radial blade, plain, there is no curvature, where the blade outlet angle is 90 degree, and the relative velocity, here also the relative velocity matches this angle, the relative velocity is 90 degree, that means 90 degree to the tangent, matching the outlet blade angle. Here the blade is in this shape, where the curvature is in the opposite direction of the rotation. This side is the curvature, that is known as backward facing or backward curved blade. This type of blades are usually preferred, that I will come afterwards, I will tell you. And here the velocity triangle is like this, which we deduced earlier. We took this type of impeller blade and the velocity triangle is like that. Now you see, from these three types of blades, forward facing, radial and backward facing, and their velocity triangles, the main difference is that in this case the value of beta 2 here, this one is obtuse. You see, this is the beta 2, this is the beta 2, this is obtuse, greater than 90 degree, where the value of beta 2 is 90 degree, and here the value of beta 2 is less than 90 degree. So if you remember this formula which we derived earlier, that theoretical head is K1 minus K2Q is given by this relation, where you just recollect that K1 minus K2Q, where K1 is this and K2 is this. So depending upon the sign of cot beta 2, this will be K1 minus K2Q or K1 plus K2Q. Now you see, in case of, if you see it here, sorry, this is difficult, I am telling you, in case of forward facing blade, K2 is less than 0, because beta 2 is less than, cot beta 2 is obtuse, so cot beta 2 is negative. So K2 is less than 0, that means K2 is negative. Similarly, for radial vane, beta 2 is 90, cot beta 2 is 0. So therefore, here cot beta 2 is 0 means K2 is 0. So H theoretical is given by K1. Whereas in case of this type of blade, that is the, here we deduce that is the backward facing blade, here it is done in the opposite way, and the direction of motion, rotation is also changed accordingly. Beta 2 is less than 90 degree, that means cot beta 2 is positive, this is an acute angle. So here it is in the form of K1 minus K2Q. So if you consider H theoretical as K1 minus K2Q, then we can tell that K2 is less than 0 in case of forward facing vanes, K2 is 0 for a radial vane, and K2 is greater than 0 for a backward facing vane. So if you consider this, then we can tell for a forward facing vane, the relationship is like this, where K2 is less than 0, that means it will be K1 plus K2Q type, that means head increases with the increase in the flow rate, okay, or the discharge. In case of radial blade, cot beta 2 is 0, so therefore K2 is 0. So it is independent of the flow rate, constant head, it delivers a constant head at all flow rate. Whereas this is the case of backward facing blade, that is the blade whose curvature is in the opposite direction of the rotation, which gives a inverse relationship, decreases with Q in a linear fashion. So if now this theoretical head discharge relationships under each case is being converted to the actual one by taking into considerations of slip, step by step slip, shock loss and the frictional loss, as we did for a backward facing impeller blade. If we do it for both radial and forward facing impeller blade, the curves will look like this. Let me show you the curve. Okay. The curve will look like this. This is finally the curves which will come. Now, for a backward facing blade, already we got this curve earlier. This looks like this. Then this will be the radial one, and this shape is for forward facing blade. But we are not discussing much about these two, since we use mostly these backward facing impeller blades in practice. The reason for this I will tell afterwards. And along with these curves, the power versus discharge also is shown like this. This is for a backward facing blade, which is very important and has a maximum at a particular flow rate, which is typically the design flow rate, and for other two, this radial and the forward facing blade, the power monotonically increases with Q. So, it is very important to explain this power and the head discharge, power discharge and head discharge characteristics to know that why the backward facing impeller blade is useful and important in practice. That I will discuss afterwards. So, today in this lecture it is up to this only. Thank you.